Hello everyone and thank you for watching this video lecture. In this lecture, I want to talk about hypergeometric distribution. The hypergeometric distribution is also in the category of discrete probability distribution, and we employ this kind of distribution to model the number of sixes in a sample drawn without replacement from a finite population. In this tutorial, we will cover definition of hypergeometric distribution, properties, mathematical formulation, and also we will go for practical examples with Python coding. So first is hypergeometric distribution. The hypergeometric distribution describes the number of sixes in a sample of size n drawn without replacement from a population of size with k sixes. And absolutely we have n minus k as failure. Unlike the binomial distribution, the trials are not independent. This is due to the lack of replacement. For example, drawing cards from a deck or sampling defective items from a batch. Imagine you are picking marbles from a bag. The binomial distribution is like picking marbles with replacement. It means after you pick one, you put it back. So the chances of getting a certain color stay the same for every pick. However, in the case of hypergeometric distribution, it's like picking marbles without replacement. Once you pick a marble, it's gone. So the bag changes and the chances of getting a certain color shift with each pick. If I want to give you the key difference between binomial and hypergeometric, in binomial we assume with replacements, or you can say a very large population, so trials are independent and the sixes probability stays constant. However, in case of hypergeometric, there is no replacement. So the probability of sixes changes with each draw and trials are dependent here. So in summary, in the case of binomial, we go with replacement. In case of hypergeometry, without replacement. In binomial, trials are independent. In hypergeometric, trials are dependent. In binomial, the sixes probability is constant, uniform, but in case of hypergeometric, sixes probability changes with each draw. So here you can see the key parameters for hypergeometric distribution. We define the hypergeometric distribution based on these parameters. N is the total population size, and absolutely n is an integer greater than 0. Then we have k, the number of sixes in the population, and it's an integer between 0 and n. And then we have n as the sample size, also it's an integer between 0 and n. And our random variable here is number of sixes in the sample. Next, we go for PMF, or probability mass function. The probability mass function of hypergeometric random variable like x is defined as px is equal to k. K here is the number of sixes in sample, and this combination of k and k is the number of ways to choose k sixes. Then combination of n minus k and small n minus k is the number of ways to choose n minus k failures, and combination of capital N and small n is total ways to choose n items. And in here our k ranges from max of between 0 and n minus k and mean of n and k. So in the same way, we can go for CDF, cumulative distribution function. CDF for hypergeometric distribution gives the probability that the number of sixes in a sample is less than or equal to a specific value. In this case, we can write CDF as f of x is equal to probability of x less than or equal to x. And this simply is equal to k is equal to max of 0 n minus k up to x, right? And probability of x is equal to k. And this probability of x is equal to k is exactly this one, PMF, right? So we can go for sum of this PMF and we call it as CDF. So here is an example for a deck of 52 cards and we have absolutely 13 hearts. We draw 5 cards. So deck is 52 cards and our N is 52. Our focus is on 13 hearts, so K is equal to 13. And we draw 5 cards, so a small n is equal to 5. Now I want to find the probability of x is equal to 2. It means when I draw 5 cards, what is the probability that 2 of them are hearts? So based on the equation, probability of x is equal to 2 is equal to 13 here k and 2 small k 2, then combination of 52 minus 13, right? It will be 39 and 5 minus 2 is 3, right? Divided by capital N 52 small n 5. Probability of x is equal to k is equal to combination of k and k, combination of n minus k and n minus k divided by n and n. So based on the combination calculation, as you know already, 13 factorial divided by 2 factorial, 11 factorial for this one. Then for this one, we have 39 factorial, 3 factorial, 36 factorial. And for this one, we will go for 52 factorial, 5 factorial, and 47 factorial. If you do all this calculation, finally you will come up with approximately 0.2743, right? So this is the probability that 2 of the 5 drawn cards are hearts. Next, we go for the expected number of sixes or mean. Simply, we can say Ex is equal to n multiply k by n. You can say the sample size, this is the sample size, multiply the proportion of sixes, k divided by n. And variance, the variance accounts for dependence due to sampling without replacement, and it is n multiply k divided by n minus k over n minus n divided by n minus 1. N minus n divided by n minus 1. This term is the finite population correction factor. We call it as finite population correction factor. The hypergeometric distribution can approximate the binomial distribution when n is too large and n divided by capital N is small. It means sampling fraction is low. In this case, we can say probability of A. So do you remember the PMF for binomial? It was equal to combination of N and K, probability of success in power of K, probability of failure in power of N minus K, right? So if the proportion of sample size to the total population size, so this is sample size and this is total population size. So if our population size is very large and proportion of sample size to the total population size is very low, then we can write in a form of binomial. So the geometric distribution can be written as probability of x is equal to k, approximately combination of n and k divided by n in power of k, like this one, and 1 minus failure in power of n minus k. We can conclude that the hypergeometric distribution is ideal for finite population where sampling affects probabilities. This is, we can say, somehow it's opposite side of binomial, because in binomial we have the choice of replacement, and also in Poisson that later we will study, we have infinite approximation. But in case of hypergeometric distribution, we can use it for the cases when we have finite population and the sampling affects probabilities. Okay, now let's go for Python coding. So for coding of hypergeometric in Python, we need to import NumPy for numerical operations and random sampling. So we go for NumPy and we will import as NP. Also for plotting, we will import matplotlib.pyplot as PLT. And also in Scipy.stats, we have Hypergeom and we can import it for hypergeometric distribution functions. From Scipy.stats, we import Hypergeom. Great. Next, we wanna go for simulation. So we will set random seed for reproducibility, and we can go for random in NumPy. So random dot seed and 42. This ensures consistent random numbers across each run. So our parameter n is equal to, for example, 20. This is the total population size, and k is equal to 7. This is number of sixes in population, and small n is equal to 5. This is the sample size, and number of simulation, for example, is equal to 1000. So these are our parameters. We can generate hypergeometric random samples. Data equals to hypergeom.random variables, and we will pass our parameters n, k, n, and size is equal to n of samples. In here, we simulate n samples from hypergeometric of n, k, and n, right? Now we can calculate mean and variance. Well, mean is equal to np.mean, mean of data. So we can print a sample mean, and in here mean is 1.76. Then we can go for variance. Variance is simply np.var of our data, and we can print it. Sample variance is variance, and it is 0.91. So we can also calculate the proportion of sixes. P is equal to k divided by n. This is the proportion of sixes. And also we can go for finite population correction factor. FPC is equal to n minus n divided by n minus 1, right? We can also print this P here. Can print PC 0.78. We can go for theoretical mean, print based on the equation that we have, theoretical mean, and this is easily equal to n multiply p, and we can go up to like 3f, right? It's 1.75, and also we can print the theoretical variance. So variance based on equation n multiply p multiply 1 minus p and multiply this fraction that we have calculated here, FPC. This is the finite population correction factor, right? So FPC, and we can go up to like 3f. It is 0.898. We can also plot the histogram of our simulated data. PLT figure fixed size is equal to 8 and 6. So in here, then we go for plt.histogram, and here we will get data, and beans is equal to range of max of our data plus 2. Color is equal to black, and transparency alpha is equal to 0.8, and density is true, and label is simulated. So this is our histogram of hypergeometric with n is equal to 20, k is equal to 7, and small n is equal to 5. We can also add the PMF. So for that one, first we need to go for x, and we will generate some x-axis range from 0 to mean of n and k. So NPA range of 0 and mean of n and k plus 1. Then we will calculate PMF. PMF is equal to hypergeom dot PMF and x, n, k, and n. These are the parameters. Then we can plot it. PLT plot x PMF, and in here like red color. And we also can label it as theoretical PMF. Right, so here we go. This is the red one is theoretical PMF, and this one is simulated. We can plot for different k values. For example, k values equal to like 3, 7, and 10. Then same, we will generate x range. X is equal to np a range of 0 and n plus 1. This is the x-axis range up to n. Then we can go for PLT figure, and fixed size is 10 and 6. Then for k in k values, PMF is hypergeometric of n. We loop our k values, and in here we compute PMF for each k. Then we can plot, so PLT dot plot, and in here x PMF, and for example we go for O dash, and this is for a style, line style, and the label is equal to like fk and k. Label equals to fk and k, and marker size is equal to a. This will plot PMF with markers like plot title and plot grid. And this one should be this one, and this thing should be out. Label. So here we can see this is the PMF for k is equal to 3, the blue color, orange color is k for 7, and green color is for k 10. Next example, during a particular period, a university information technology office received 20 service order for problem with printers. Out of these 20, 8 were laser printers and 12 were inkjet printers. A sample of 5 of these service orders is to be selected for inclusion in a customer satisfaction survey. Suppose that the 5 are selected in completely random fashion, so that any particular subset of size 5 has the same chance of being selected as does any other subset. What is the probability that exactly x is equal to 0, 1, 2, 4, or 5 of the selected service order are inkjet printer? We will write the parameters. Capital N is equal to 20, and this is total service order. Sample size is n is equal to 5. This is our sample size. 12 are inkjet, right? So we can say m is equal to 12. This is number of inkjet printers. And n minus n, 20 minus 12 is equal to 8. And this 8 is the number of laser printers, right? So the probability here is given by the hypergeometric distribution. For example, the probability that exactly 2 of selected service orders were for inkjet printer, with like for example px is equal to 2, is hypergeometric of 2, then here 5, 12, and 20. What is this one is simply number of outcomes having x is equal to 2 divided by number of possible outcomes. Number of possible outcome, right? So we can write Px is equal to combination of 12 and 2, combination of 8 and 3, and combination of 20 and 5. So in here, these 12 and 2, this is the number of ways to choose 2 inkjet printer from 12 that we have here. This 8 and 3 is the number of ways to choose 3 laser printers from 8. And 5 and 20 is the total number of ways to choose 5 service orders from 20 service orders we have. So if you do this calculation, this is simply 12 factorial divided by 2 factorial, 10 factorial. This is 8 factorial divided by 3 factorial, 5 factorial. And this one is 20 factorial divided by 5 factorial, 15 factorial. So if you do this calculation, you will come up with 77 divided by 323, which is approximately 0.238. The probability that exactly 2 of the selected service orders were for inkjet printer is 23%. We can code it in Python. What are the parameters? M, N, and N, right? So our M is simply equal to 20. Our small n is equal to 5 and capital N equal to 12, right? Then x is equal to hypergeom, and in here we will pass M, N, and capital N. We can calculate PMF. We need to generate some values. So we can write np.arange, a range from 0 to n plus 1. And we can calculate PMF. PMF is equal to x.pmf of x. So this should be capital X. So you can see here, these are the values that we have generated as PMF for this range, right? It means up to 5, 0 to 5, right? And if I want to print only for 2, so it is something here, right? This is 2 first, so this is for 0, 1, and 2. Or I can say print x.pmf of 2, which is a 0.238. Also, I can plot it, right? For example, I can say fig is equal to plt.figure and x is equal to fig.add subplot. Then in here, x.plot, I will get x, PMF, and for example, blue, and this one. Then I can go for vertical lines, x.vertical lines, and I will pass x, 0, PMF, and L2 is equal to 2. So here it is. Here we created a new figure object which serves as the canvas for the plot. Then in here we add fig.add subplots. Here we add a single subplot x to the figure and we define the plotting area. This 1, 1, 1 is a shorthand for 1 multiply 1 grid. It means 1 row, 1 column. With the first subplot, we have, x dot plot x PMF and BO. This is for plotting the PMF values as points that you can see here. Blue is here, right? If I change this one to R, then you can see this will be red color. So this is a V line. It is a method object for this vertical line that we have here. And this LW is equal to 2, specify the line width as 2 points. Let's go for another example. 5 individuals from an animal population thought to be near extinction in a certain region have been caught, tagged, and released to mix into the population. after they have had an opportunity to mix, a random sample of 10 of these animals is selected. So if X is the number of tagged animals in the second sample, suppose there are actually 25 animals of this type in the region. What is the probability that X is equal to 2 and X is less than or equal to 2? This one follows a hypergeometric distribution. So this one is N, capital N. This is the total population size. And we say that 5 individuals from an animal. So we can write K is equal to 5. This is number of tagged animals, or you can say sixes. And a small n is equal to 10. This is the sample size. So in this case, our PMF is hypergeometric of X, 10, 5, and 25, right? Based on the equation, we write probability of X is equal to K is combination of K and a small k, this is capital K, n minus k divided by combination of n and n. Based on this equation, 5 and x, combination of 5 and x, because we are going to x for 2 and x less than or equal to 2. So 5 and x, 20, right? So because it's 25, 25 minus 5 is 20, and 10 minus x, n minus k, divided by combination of 25, capital N, and a small n, 10. So for the first case here, hypergeometric of x is equal to 2. Hypergeometric of 2, 10, 5, and 25, which is equal to 5 and 2, 20 and 8, 10 minus x, right? And 25 and 10. And then if you do this calculation, then you will come up with 0.385. Then the probability of x less than or equal to 2 is the probability of x is equal to 0, 1, or 2. 0, 1, or 2, right? So we can write this one as sum of x is equal to 0 to 2, hypergeometric of x, 10, 5, and 25. Once we put 0 here, second time we put 1 here, and third time we put 2 here. So for 0, it will be something like 0.057, plus for 1, it will be 0.257, and for 2, we already calculated 0.381, which is 0.699. So in here, we calculated this equation for 0, 1, and 2, right? So this is for 0, this is for 1, and this is for 2, right? It means combination of 5 and 0, combination of 20 and 10. And 25 and 2. For the 1, combination of 5 and 1, 20 and 9, 25 and 10. And for 2, that we already calculated here. So it will be something like 0.699. So let's do coding for the same problem in Python. So we define our parameters. N is equal to 25. This is the total population size. K is equal to 5. This is the number of tagged animals, or you can say sixes. And a small n is equal to 10. This is the sample size. Then we go for probability of x is equal to 2, right? So I can write P2 is equal to hypergeom.pmf, and in here I will pass 2, n, k, and n, right? This will compute PMF for x is equal to 2 using hypergeometry. So we can print P2, so it is 0.385. Then I can go for x less than or equal to 2. For that one, then I will go for x values. I write x values equal to np dot a range of 0 to 3, because we want to go for 0, 1, and 2. Then I will calculate PMF values, and this PMF values is hypergeom, and this time, so in here we only consider 2, but this time we will go for these x values, right? Hypergeom PMF, and in here x values and n and k and n, right? Then we will calculate for every one of them. So I can say p like less than or equal to 2 is equal to np dot sum of PMF values, right? Then I can print PLE2, which will be sum of them is 0.698. This is the same that we did here. Thank you very much for watching this video lecture. In this lecture, we studied hypergeometric distribution for discrete random variables. We studied definitions, parameters, PMF, CDF, mean, variance, several examples, and also we practice in Python. Please feel free to ask me your questions by leaving a comment below this video lecture. Thank you and see you in the next lecture.